Welcome to Friday, March 15th lecture for linear circuits. This is the first lecture which will cover the basics of doing the impedance method. The slides for this will also be posted, so you can watch this video and have the slides up at the same time if you'd like, and feel free to pause the video as often as you'd like. Here we go. So the impedance method is a general method to find the differential equation that is reflected by the circuit you're studying. It's kind of just a shorthand way of not having to write d by dt all the time, is basically what it is. So instead of doing that, we write s for the time derivative, and then we can still use Ohm's law, which relates current and voltage for every device. But now instead of being a simple Ohm's law V equals I times R, we're going to use this complex impedance to represent the kind of encode the information about the time dependence relationship. So for an inductor, we're going to do an impedance Z equals SL, and that comes from the equation that says V for an inductor equals L dIL dt. If we change that, instead of writing d by dt, we just write an s that says that V for an inductor equals Ls times I. And then if you look at how this compares to like an Ohm's law equation, the L and S are kind of like the resistance for a resistor. So we're going to call that the impedance. If you do the same thing for a capacitor, you start with the relation that IC equals C dVC dt. Then that tells you that IC equals C times S VC, where S is the derivative. And then rearranging that to be V equals something times I, you get VC equals 1 over SC times IC. So the kind of the Ohm's law resistance, which we call the impedance for a capacitor, is 1 over SC. What that really means is the voltage is the integral of the current, because 1 over S is like doing the opposite of the derivative, or taking the integral. So what you do is you change all the devices to impedance devices, and then you can analyze the whole circuit just like we would have done before with resistors. So you do nodal analysis, mesh analysis, etc. Once you've done that, you can you can rearrange everything to get a final form for the differential equation, and then use that to find the form of the solution. So let's see how that plays out on an actual circuit. So here's a very basic circuit. Note here there's a resistor, an inductor, a capacitor, another resistor. It's not the basic series RLC or parallel RLC form, so we're going to have to use some method to find the differential equation. We could do that by writing mesh and nodal analysis and keeping track of all the d by dt's, but instead of doing that, we're going to use this impedance method. So first note, there's a voltage supply there. That will determine the initial conditions and the steady state conditions, but it won't determine the characteristic equation of the differential equation. So the we call it the topology of the circuit is what determines the actual characteristic equation. And then all voltage supplies are inputs to the system, which determine initial conditions, etc. So let's start by analyzing the circuit with no voltage supply on. So if you remember, when we turn off voltage supplies, we replace them with a wire. And then let's write down the impedance of each device. So for the resistor, it's just Z equals R. For an inductor, Z equals S times L. And for a capacitor, Z equals, for the capacitor, Z equals 1 over S times C. So I should have gone to this slide first. So if we write like a nodal analysis at, say, this node on the top right here, we could say all the currents leaving this node sum to 0. That would mean this current plus this current plus this current all sum to 0. And just like we did with Ohm's law, we then translate that into be in terms of the voltages. So here is, I guess I'll label down, this is let's call this I1, I2, and I3. Here is I2 plus I1 plus I3, all sum to 0. So it's just like we did before with resistors, but now the equivalent kind of resistance, I've got quotation marks up here, is like the impedance of the device. So for a resistor, it's still R. For a capacitor, we're going to plug in it's 1 over SC, and for an inductor, it's going to be S times L. Okay, so note what we've done here first is we've turned off this voltage supply because we're using this method just to find the characteristic equation that represents the circuit itself with no inputs on. So there's just a wire there to replace that voltage supply. Now we can plug in what are the impedances of all these devices. So for a resistor, it's just R. For a capacitor, it's 1 over SC. And for an inductor, it's LS. So here's the capacitor. Here's the inductor. And then with a little rearranging just to get that C1S out of the denominator, I have this expression. Now note this represents the differential equation for the voltage at that top right node. To get it in a standard form, we want to get rid of all the s's in the denominator, so we can multiply through by that denominator R1 plus L1S. So multiply through both sides. There's a 0 on the right, so that makes it easy. And feel free to pause the video or take your time to work it out, but we can quickly find what the differential equation is for this, or the characteristic equation is for this circuit. So for, I guess going from this step to this step, I plug in what the values of R and L and C are. Do a little simplification to get here, and then one more simplification, and we get here. In a standard form, we want the S squared term to have a 1 in front of it. So multiply through by 2, and here we get a standard form for the characteristic equation of the system. So note this does not have the voltage supply on. It just says how does this circuit respond to any kind of input, and it's in this form. So now that we have it in this form, we could say as the characteristic equation here, we can compare this to the standard form to find what alpha and omega are for this circuit. So the standard form is in S squared plus 2 alpha S plus omega naught squared equals 0. Therefore, in this case, 4 equals 2 alpha, so alpha is 2, and 6 equals omega naught squared, so omega naught is root 6. So alpha is 2, omega naught is root 6, which is bigger than 2, so therefore it's underdamped. Okay, so we could do the exact same analysis. You may go through this slower in the PDF posted slides if you'd like, but basically what we do is I'm just showing here that mesh analysis would get you to the same result. So writing a mesh equation around the mesh on the left and then the mesh on the right, and combining the equations into one, then getting it into standard form, you're going to end up with the exact same characteristic equation. So it doesn't matter how we analyze the circuit, this same characteristic equation comes up all the time. And that's because any variable you look at in the circuit is going to respond in an underdamped fashion with these alpha and omega naught values. That's kind of neat. So to finish this problem off, we could, if we wanted to, find the full form of the solution. We know that it's underdamped. And so say we're trying to find that voltage at node 1 up here, call this V1. And if this is ground here, so V1 with respect to ground, we could say that V1 at T is going to be e to the minus alpha t times a cos omega dt plus b sine omega dt. And that would be if the voltage decays away to nothing. But because we have this voltage supply Vs here, the final voltage may not go to 0. So there has to be like a steady state final value. So we put a plus V steady state there. Then we could plug in alpha. We have that. We have omega d. And then we can apply initial conditions to find A and B, and the final condition to find VSS. So really quickly, just to find when it reaches steady state, let's say that Vs is just a constant value that's been on for a very long time. At steady state, the inductor would act like a wire, the capacitor would act like a gap, and you'd have kind of a voltage divider law there. So VSS is going to equal V steady state is going to be that voltage source times R2 over R1 plus R2. So that you can plug in right away for that term. And then you can plug in when time equals 0, what is the initial voltage, and when after a long time, or sorry, then the other, to find the other constant, you need to take a rate of change of the voltage of the capacitor. But we'll do that in some more examples right away. So the next few videos are going to be about the problems. I'm going to actually just separate these into separate videos in case people want to watch them on their own as they're doing the homework set. So that concludes the first video.